Free fall. In this video, we will learn about the fundamental principles of free fall, including the constant acceleration due to gravity. We'll discuss what it means for an object to be in free fall and touch on why mass doesn't matter without air resistance. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It is very important for the continuity of this channel. Free fall is the motion of an object at which its weight is the only force acting on it. This means that an object in free fall is accelerating at a constant rate due to the pull of gravity, and this acceleration is the same regardless of the object's mass, assuming there is no air resistance. A classic example used to illustrate this is dropping a feather and a bowling ball in a vacuum. Since air resistance is not a factor, both objects will fall at the same rate and hit the ground at the same time. On Earth, the acceleration due to gravity is approximately 9.8 meters per second squared. While free fall describes motion with only gravity acting on an object, the real world introduces another significant factor: air resistance. Air resistance, also known as drag, is a force that opposes the motion of an object as it moves through the air. The amount of air resistance an object experiences depends on several factors, including its speed, shape, and surface area. A bowling ball and a feather have very different characteristics when it comes to air resistance. The feather has a very large surface area relative to its mass. This means that as it falls, the air pushes up against its wide surface, creating a significant amount of drag that slows it down. The bowling ball, on the other hand, is heavy and dense with a small surface area. The force of gravity on the bowling ball is much greater than the opposing force of air resistance, so the ball's downward acceleration is only slightly affected. Therefore, because the feather experiences much more air resistance relative to its weight than the bowling ball does, the ball is able to accelerate more freely, reaching the ground first. If this experiment were conducted in a vacuum, a space with no air, you would see that the ball and the feather would hit the ground at the exact same time, as the only force acting on both would be gravity. The equations for free fall are a specific application of the kinematic equations used to describe motion with constant acceleration. In free fall, the constant acceleration is the acceleration due to gravity. Assuming the downward direction is positive, the primary equations are final velocity. This equation relates the final velocity to the initial velocity, the acceleration due to gravity g, and the time t the object has been falling. If the object is dropped from rest, the initial velocity is 0, and the equation simplifies too. Distance or displacement. This equation calculates the distance d an object has fallen based on its initial velocity, the time, and the acceleration due to gravity. If the object is dropped from rest, the initial velocity is 0, and the equation simplifies too. Final velocity squared. This equation is useful when you want to find the final velocity without knowing the time. It relates the final velocity to the initial velocity, the acceleration due to gravity, and the distance of the fall. If the object is dropped from rest, the initial velocity is 0, and the equation simplifies too. These equations are most accurate when air resistance is negligible. Let us see how freefall works. An object falls from a hovering helicopter and hits the ground at a speed of 30 meters per second. How long does it take the object to reach the ground and how far does it fall? The object falls from a hovering helicopter. This is a crucial detail. Hovering means the helicopter is stationary, so the object's initial velocity is 0 meters per second. The object hits the ground at a speed of 30 meters per second. This is the final velocity. This is a free fall problem, so the acceleration is due to gravity. The constant acceleration is 9.8 meters per second squared. How long does it take? This is the time t. Now let's look at the free fall equations and decide which one will help us find the time. The first equation includes all the variables we have. It also has the variable we need to find, t. This is the perfect equation to start with. So we take the first equation and solve for t. Now that we have the time, we can use it to find the distance. How far does it fall? This is the distance or displacement. We have two equations that can be used for this. Both will work, but using the second one is a good idea. This way, if there was a mistake in the time calculation in the previous step, it will not affect the distance calculation. It's a way to check your work. So we use the third equation and solve for distance or height. Let us see another example. A stone falls from rest from the top of a high tower. Ignore air resistance and take g equals 9.8 meters per second squared. What is its speed after 4 seconds? How far has it fallen after 3 seconds? A stone falls from rest. This is the most important piece of information. From rest means the initial velocity is 0 meters per second. Ignore air resistance. This tells us we can use the standard free fall equations. What is its speed after 4 seconds? We need to find the final velocity when the time is 4 seconds. The first equation is perfect for this. How far has it fallen after 3 seconds? We need to find the distance when the time is 3 seconds. We need an equation that connects distance, initial velocity, acceleration, and time. The second equation is the most direct way to solve this.